The diagram you're looking at is called a fault tree. It's a graphic depiction of events leading to a system's failure. It is a common tool used by safety professionals, used by engineers. What we have here in the fault tree, again, this is a very simple fault tree, just to illustrate a fault tree and how it can be used to calculate the probability of failure in a system. But what we're doing in a fault tree, we are showing the events leading up to what we call the top event. In this case, the top event is an unsafe atmosphere. Again, all the events leading up to it. We have basic events. Basic events are the circles. Then we have intermediate events. And pardon my penmanship, it's not that great. But we have basic events and intermediate events. We also have logic gates showing how these different events are connected and can result in the occurrence of the top event. We have OR gates and we have AND gates. The AND gates mean that both of these events must occur for this intermediate event to occur. Fan failure and backup fan failure must occur before we're going to have pressure failure. The OR gates mean that any of these four events, if any of these four events occur, we're going to have exhaust failure in this particular example. Also, in this fault tree diagram, we have the probabilities available for the basic events. With the probabilities and the logic gates, that allows us to calculate the probability that the top event will occur. All right, let's go ahead and look at this example problem. Again, this is a simple example, but we have a manufacturing operation using a local exhaust ventilation system with a replacement air supply to protect personnel from potentially harmful atmospheres. Proper functioning of the system allows workers to perform without using awkward respirators or other personal protective equipment. Based on information in the fault tree, what is the probability of conditions in the work atmosphere requiring workers to don escape respirators and evacuate the area? Or in other words, what is the probability of an unsafe atmosphere occurring based upon the different basic events, intermediate events, and how they are related and can result in the top event. All right, well, let's go ahead and calculate the probability of an unsafe atmosphere. Okay. Now we'll work from the top down, and normally when you're doing some kind of fault tree analysis, you're working from the top down. You start with the top event and work down back to the basic events. It's a deductive reasoning approach to understanding safety in a system. But we start with the top event, an unsafe atmosphere. An unsafe atmosphere will occur if we have exhaust failure or we have replacement air failure. If either of those events occur, we're going to have an unsafe atmosphere. And that can be depicted in this formula. Again, going back to the addition rule. Anytime it's an OR situation, we add the probabilities. The probability of an unsafe atmosphere equals the probability of exhaust failure plus the probability of replacement air failure. But we don't have the probabilities for exhaust failure and replacement air failure. So we need to work further down the fault tree to the basic events where we have those where we have those probability values. So we need to find the probability of exhaust failure. And here's our formula for the probability of exhaust failure. Again, applying the addition rule because it's or. If any of these events occur, we'll have exhaust failure. So exhaust failure is probability of pressure failure, duct failure, hood failure, or stack failure. Any of these occur, we have exhaust failure. And now for three of these different conditions, we have, they're basic events, and we have the probability values. But for pressure failure, we don't have that. That's considered an intermediate event. We have to go back a little further to find the conditions leading to pressure failure. And pressure failure, I'm getting a little ahead of myself here. Ignore this for the moment. Pressure failure is the probability of primary fan failure and backup fan failure. Both of these have to occur for pressure failure to occur. The reason I'm using the term pressure is kind of a sidebar. That's what a fan does. A fan creates a pressure differential that allows air movement. So when a fan fails, we don't have the pressure differential, we don't have the air movement. So again, we have a primary and a backup, both have to fail. So the probability of pressure failure will be this probability multiplied by that probability, 0.004 multiplied by 0.004. We can bring this back up to this formula. We have 0.004 times 0.004 for pressure failure, plus duct failure, which is 0.00085, plus hood failure, 0.003, plus exhaust stack failure, which is 0.1. And that's everything we need. We do the math there, we do those operations, we end up with a probability of exhaust failure of 0.1039. So that's 1/2 of what we need to calculate the probability of an unsafe atmosphere. But we need to go over on the right side of the fault tree and look at replacement failure. We need to calculate the probability of replacement air failure. Again, there's the formula for probability of replacement air failure. It's probability of pressure failure plus duct failure plus contaminated air failure. If we have our intake for the supply system too close to the exhaust stack that's spewing out the contaminated air, we might draw the contaminated air back into the ventilation system. So, just like on the left side, we have everything. We have duct system failure probability and contaminated replacement air probability, but we need to find the pressure failure probability. Again, intermediate event that's preceded by these basic events. And the same fans are being used for the supply system that's being used for the exhaust system, so the probabilities are the same. Same setup, same model of fan, same everything. So probability of pressure failure on the replacement side, 0.004 times 0.004. Bring that back up to this formula. We end up with 0.004 times 0.004 for the probability of pressure failure, plus the probability of duct failure, 0.0085, plus the probability of sucking in contaminated air, 0.007. Now we just do the math here. When we do that, when we perform those mathematical operations, we end up with a probability of replacement air failure of 0.0709. Now we can bring everything back up here. The probability of an unsafe atmosphere is 0.1039 plus 0.0709. Remember this, it's an OR situation. If it's OR, we add the probabilities. 0.1039 plus 0.0709. resulting in a system's reliability probability, or a probability of failure for the system, of 0.1748 or 17%, which is really too high. There's a 17% chance that we'll have a ventilation failure resulting in unsafe conditions. And this illustrates another value in fault tree analysis. Once we have our probabilities, we can go back up and look at the basic events and the probabilities of failure for these basic events and these basic components. And we look for areas where we can tweak the system to lower the risk, to lower the probability of failure. One common mistake or deficiency with ventilation systems is the installation of the exhaust stack. There are a couple of variables that have to be considered that often get overlooked. They may not be overlooked by the engineer that designed the system, but they may be overlooked by the crew that's installing the system. But the two primary variables are the distance of the stack outlet above the roof line. It has to be high enough. Also, you have to take into consideration the wind speeds, the prevailing winds in the area, and how those winds create turbulence. If the winds are just right, they can create a turbulence that can keep all of the bad stuff that we're trying to exhaust in the system. It won't exhaust properly. Again, these are maybe the most common problem with exhaust ventilation systems is the installation of the exhaust stack. Another issue that you can take a look at would be the capture hood, the type of capture hoods that are being used to suck in the contaminated air at the source. Some capture hoods are more efficient than others, and the way the capture hoods are installed can also affect the efficiency of the system. So if we had this probability, one thing we'd want to do is go back and look at tweaking the exhaust stack setup and maybe the capture hood setup. We could also look at maybe going with a more reliable fan system to lower the probability. But this is going to give us our biggest bang for the buck as far as lowering the probability of this system's failure. All right, one more slide I want to show you. Actually, I'm not going to show you that slide. I will end by saying that there are real-world applications for this methodology. Also, you are likely to see this on the CSP exam when you're ready for certification. Let me know if you have any questions.